Dr. Ludwig Friedmann. I would like to introduce him to you. He will present the test and analysis task description, and in his career he's a solution architect for simulation for autonomous driving, and at set level you are responsible for the development of abstract test specification and 3D models and material. You also engage in invited academy, presenting certificated courses as well. And you are also very fond of open material, 3D models and exchange on GitHub, for example.
Sure.
The stage is yours. Thank you very much.
Thanks a lot for the kind introduction, Laura. Well, hello everybody. As Laura just said, my name is Ludwig Friedmann from BMW. Welcome to this third presentation of the session. I'd like to present you a novel approach on the specification of test and analysis tasks today. To be more precise, I'd like to give you a brief introduction in a formalized way to specify requirements and abstract descriptions of test and analysis tasks based on ontologies. The presented approach touches two areas of the project: methods and standards. If you remember our presentation from the halftime event, which was about a consistent test case description, this was now extended by a method for formalization of requirements and abstract test and analysis tasks based on ontologies. Goals of the method developed was to enable homologation, where requirements originate from central authorities, to enable industry-wide exchange of unambiguous and consistent test and analysis task descriptions, and to improve communication in daily business, where ambiguity often leads to misunderstandings. The development of the above-mentioned method clearly aims for standardization, as it's based on existing standards, such as the ASAM test specification group results and ASAM X ontology. Therefore, we clearly propose continuation of those projects based on our results. But first, let's start with a simple example to understand why formalization is needed. Here's a simple example of a requirement in a test task. The potential requirement behind the example could be the ego vehicle's ACC should maintain a longitudinal distance of 60 meters from the vehicle in front of it. To derive an unambiguous and consistent test case description from that requirement, we need more information. For example, in which situation should this be tested? What kind of traffic participants are involved? What does the road look like? At what speed do traffic participants travel? How are they positioned to each other? How long should the test run? And much more information that's not listed here. For example, on which test platform should the test run? Which models should be involved? The overall question coming up is, how can it be ensured that the information specified within this requirement is complete and there's no misinterpretation when exchanging or interpreting it? To make things worse, let's have a look at the problems arising from involved workflows, people, and processes. Here's a brief overview of the underlying process of automotive testing. First, requirements or KPIs or analysis goals are defined. From the requirements, test and analysis tasks are derived. After their execution, test results are evaluated and aggregated. Finally, KPI results are formulated. Here, different groups of people are involved. KPI and analysis specialists, specifying KPIs and requirements and checking for their fulfillment. Test and analysis developers, deriving test and analysis task descriptions based on requirements and individual expert knowledge. And finally, test and analysis managers, aggregating the results of test and analysis series and evaluating them. Moreover, various software tools, which are even not depicted here, are used. There's requirements management software, test management software, test execution software, simulation software, and all of them may be running on various test instances. So based on the simplified schematic representation, it becomes even clearer that the derivation of unambiguous and exchangeable test and analysis task descriptions based on given requirements requires certain formalism. But how can this formalization be acquired? To answer this question, we first went on a search for existing building blocks. We found what we were looking for in the domain of scenarios of driving simulation. Very similar to the different levels of test and analysis task descriptions, from functional natural language requirements to concrete machine-readable test descriptions, levels of abstractions have been derived for scenarios. There's a functional level with describing non-formal human-readable scenarios. There's an abstract level, which is kind of a formalized machine-readable description which may already contain constraints. There's a logical level, which is kind of a parameterized representation of a set of concrete scenarios. And finally, there are concrete scenarios, which are typically single scenarios with fixed parameters. Each of these levels has its own use case, from human-readable early sketches to machine-readable execution instructions. To achieve exchangeability and unambiguity, it has to be ensured that concrete scenarios executed on computers precisely represent the intentions behind the human-readable informal counterpart. The concept of formalization that ensures this kind of consistency can be based on ontologies. What are ontologies? Ontologies are formal machine-readable representations of knowledge in a specific domain. The most prominent example in the domain of traffic simulation comes from the ASAM OpenX ontology project. Results of this project served as a foundation for our formalized approach outlined on the following slides. As mentioned before, concerning formalization of test and analysis task descriptions, we identified existing building blocks within the domain of driving simulation scenarios. Here, ways and means already exist to derive logical or concrete scenarios from abstract scenario descriptions. As said, underlying formalization concept is provided by the ASAM OpenX ontology project. As an example, an important concept within ontologies is that combination of a subject, an object, and a relationship between them results in a directed triple, subject, predicate, object. This concept enables identification of conflicts and logical incoherencies, and even helps to infer additional relationships not explicitly stated. Besides formalization concepts, software tools for ontology development are already in place. For example, there's the open source project Protégé providing a powerful ontology editor based on Web Ontology Language 2.0. Unfortunately, for the formalization of abstract test and analysis task descriptions, currently no concept exists. On the following slides, we'll outline the approach we took, which, based on the mentioned building blocks, tries to eliminate this shortcoming. But first, we have to understand how ontologies actually work. Ontologies are formal, machine-readable representations of knowledge in a specific domain. They are used to represent knowledge in a way that both humans and computers can understand. To do so, they leverage standardized definitions of concepts. Ontologies also describe how defined concepts relate to or differ from each other. In this way, they enable humans and machines to use logical reasoning to infer additional knowledge. Ontologies define concepts such as classes and corresponding class members, individuals. In addition, they define properties which express relationships between class members. Relationships are directed. They point from a subject to an object. Classes and properties from directed graphs with classes form a directed graph with classes as nodes and properties as edges. This kind of graph is called a T-box, where T stands for terminological. Semantic applications can traverse this graph and evaluate logical characteristics. In this way, they can identify conflicts and logical incoherencies. Another graph is formed when individuals are interconnected with directed relationships. In this graph, individuals are nodes, and specific relationships are edges. This kind of a graph is called an A-box, where A stands for assertion. By applying logical reasoning to A-boxes, semantic applications can infer the existence of additional relationships. On the next slide, we see how relations can be mapped in an ontology. The combination of a subject, which may be a class or individual, an object, which may be a class or individual, and a predicate, which can be a property or a relation between them, results in a triple. Most prominent examples are RDF triples. RDF stands for Resource Description Framework. An example RDF triple could be the property has component, which acts as a predicate, connects the class road, which acts as a subject, with class lane, which is the object in this triple. This relationship could be described by a natural language expression such as a road has components that are lanes. All the same, triples can be formed by individuals. The formally given example can be translated to an assertion. Road 1 has component lane 1, and road 1 has component lane 2, resulting in 2 A boxes. These simple concepts can be scaled to entire domains. Let's see how concepts can be applied to the specification of test and analysis tasks. Let's have a look at the following text, which could be an example for a human-readable abstract test description. Evaluate on instance SIL with simplified vehicle model that the minimal Cartesian distance between objects ego vehicle and proceeding vehicle at meter accuracy, driving at initial position and velocity in the same lane on a straight road of 2,000 meters length, and check if it's larger than threshold 60 meters. Store binary true if this condition is met throughout the whole test duration of 20 seconds. Using OpenX ontology, scenario-specific passages depicted in blue can be directly translated. For example, the ego vehicle is located on lane 2. Yet, test-specific parameters depicted in red are out of scope of our OpenX ontology. These parameters have to be added in order to enable abstract test descriptions. For example, test case 1 uses scenario 1. Ego vehicle is laterally controlled by ACC 1. Or minimal distance 1 has value 60. Remember, tests may incorporate scenarios, but they do not have to. Well, let's see how OpenX ontology can be extended by test-specific content. In first place, OpenX ontology aims to structure and formalize knowledge in the domain of road traffic. By implementing modularization, OpenX ontology divides structures into individual modules for independent subject areas. Modules are the core ontology, describing or being the top-level ontology, a framework of classes and properties used as foundation for domain-specific content. The domain ontology, describing central concepts of road traffic, for example, lanes, roads, vehicles. Those kind of concepts are summarized here to ensure consistent and expressive underlying language for ASM OpenX standards. And finally, the application ontologies, which are still in the making. Here, ASM plans to develop one application ontology per OpenX standard. Application ontologies will contain concepts that each particular standard is allowed to modify independently. To extend OpenX ontology by test and analysis task-specific aspects, we added exemplary implementation of an application ontology set-level test spec ontology, based on the presented ACC example. In this way, we were able to integrate and verify the application test with OpenX ontology, complementing ODD, scenario, map, and label. On the next slide, we'll see the potential of this approach. Using the presented approach, we enabled the following applications. Consistent and common understanding of test and analysis tasks for regulators, authorities, OEMs, and suppliers. Automated checks of specifications for consistency and completeness for test and analysis tasks, requirements, and KPIs. And finally, partially automated generation of logical and concrete descriptions of test and analysis tasks, as well as database searches for models, scenarios, test and analysis task descriptions. Let's have a look at that last example because it's especially exciting. A particularly impressive yet illustrative example for our approach are database search operation. Obviously, based on ontologies, data can be searched for keywords. But there are even greater advantages of ontology usage. First of all, the common definition of concepts guarantees that all participants have the same understanding of concepts. Second, extensibility. By adhering to semantic standards and used by ontologies, participants can extend them and be assured that others will interpret them correctly. Third, rules and reasoning. The logic or theory for expressing rules in ontologies enables computer programs to infer relationships that are not explicitly stated. This can be used to assess coverage, to extract common patterns, and even find semantic errors. And finally, the determination of semantic proximity and reasoning. Ontologies make it possible to assess semantic proximity of different concepts. This enables semantic searching and matching, clustering by semantic similarity, and classification based on patterns. But only by standardized formalization, for example, using ontologies, comprehensive databases can be created and the mentioned advantages can be leveraged. Even though proprietary solutions may be readily available, they prevent collaboration and scaling of databases. This is why we are proposing further development at the ASAM OpenX Ontology project and its domain model. To sum it up, let's recap what we've seen on the previous slides. Within the set-level project, we have realized a verification of the underlying credible simulation process, CSP. For the half-term event, we've created a proof of concept for a keyword-based test specification. And finally, today, we've presented a concept for ontology-based abstract test and analysis task specification. Beyond the project, we've transferred our ideas to the ASAM test study group project. And we've implemented and extended the ontology of ASAM OpenX Ontology in our approach for formalization of test and analysis tasks. Now, as recommendation, we strongly propose, let's have a test specification follow-up project at ASAM and push cooperation with OpenX Ontology. Thanks for your patience. This is the last slide of my presentation, visualizing the takeaways one more time. I'm happy to answer your questions now. If you have further questions later or tomorrow, feel free to visit my colleague Markus Deppe and me at the booth B15 in tomorrow morning's stream.